The intent of National Electrical Code Article 240.4b is to provide flexibility when selecting circuit breakers, particularly when the conductor's current carrying capacity doesn't precisely match standard breaker sizes. This promotes economical use of materials, especially when standard conductor sizes are not available, or when increasing the breaker size avoids upsizing the conduit. The code recognizes that matching conductor ampacity to breaker ratings isn't always practical or cost-effective. For instance, consider feeding a 400 amp panel board with 500 kc mil conductors. While the 500 kc mil conductors are rated for 380 amps at 75 degrees Celsius, using the NEC standard breaker size might necessitate a larger conduit, increasing expenses. Article 240.4b offers a practical solution by allowing the NEC's larger breaker size when the conductor ampacity is less than the breaker rating. In this example, a 500 amp breaker, though rated higher than the conductor ampacity, can still protect the 500 kc mil conductors if the actual load doesn't exceed 400 amps, staying within the conductor's safe operating capacity. A key limitation of Article 240.4b is that it only applies when the conductor ampacity is less than the breaker rating and the load current remains below the conductor's ampacity. It's not permissible to use a larger breaker if the conductor size exceeds the breaker rating or if the load current exceeds the conductor's ampacity. The purpose of this rule is to allow for the use of standard conductor and circuit breaker sizes to reduce waste and unnecessary expenses. If you had a 200 amp load, you wouldn't need to use 250 kc mil copper conductors rated at 255 amps at 75 degrees Celsius, when you could use 3/0 copper conductors rated at 200 amps at 75 degrees Celsius. So using 3/0 copper conductors is much more cost effective and meets the NEC requirements. You need to follow the guidelines in Article 310.16 when selecting your conductor for the correct ampacity. The termination temperature is very important when selecting the correct wire size. Equipment is typically rated at 60 degrees Celsius or 75 degrees Celsius. Conductors must be sized according to the lowest temperature rating. If you had a breaker rated at 60 degrees Celsius, you must select the wire size based on the 60 degrees Celsius column. If the termination temperature is not identified, then 60 degrees Celsius is used for equipment rated 100 amps or less, or marked for 14/1 AUG conductors. 75 degrees Celsius is used for equipment rated over 100 amps, or using conductors 1/0 AUG or larger. Here is an example that does not meet code. If a 200 amp breaker is feeding a load that is expected to be 180 amps continuous, you would not be able to use 1/0 aluminum conductors. 1/0 aluminum conductors are rated for 120 amps at 60 degrees Celsius and 145 amps at 75 degrees Celsius. Therefore, you would have to use 4/0 aluminum conductors rated at 200 amps at 60 degrees Celsius and 230 amps at 75 degrees Celsius. Continuous load is defined as a load where the maximum current is expected to continue for 3 hours or more. Breakers and conductors for continuous loads are sized at 125% of the continuous load. This means that the 180 amp continuous load is actually 225 amps. 180 amps x 1.25 equals 225 amps. If you look at table 310.16, you will notice that for copper conductors, 4/0 AUG conductors meet this requirement and are rated for 230 amps at 75 degrees Celsius. A 4/0 AUG aluminum conductor is only rated for 200 amps at 75 degrees Celsius, and you would have to use 250 kc mil aluminum conductors that are rated for 205 amps at 60 degrees Celsius and 240 amps at 75 degrees Celsius. Also, you can parallel conductors if one conductor is not large enough. Article 310.10 says that aluminum, copper-clad aluminum, or copper conductors of size 1/0 AUG and larger can be run in parallel. For example, a 400 amp load could be supplied by 2 sets of 3/0 copper conductors in parallel. Each 3/0 copper conductor is rated for 200 amps at 75 degrees Celsius. Two 3/0 copper conductors would give you a total of 400 amps. When conductors are installed in parallel, they have to be the same length, same conductor material, same size and circular mill area, same insulation type, and be terminated in the same manner. When conductors are paralleled, the overcurrent protection is based on the total ampacity of the parallel conductors. Also, if you are bundling wires together, you have to apply an adjustment factor to the ampacity of the conductors. Table 310.15 goes over the adjustment factors for more than 3 current carrying conductors in a raceway or cable. For example, if there are 4 to 6 current carrying conductors, then the ampacity of the conductors has to be adjusted to 80% of their ampacity. If you have a cable that has 4 current carrying conductors each rated for 30 amps, the adjusted ampacity is 24 amps. 30 amps x 0.8 equals 24 amps. Derriting is not required if the conductors are in a nipple that is 24 inches or less in length. The next thing we will discuss is voltage drop. Conductors should be sized to prevent voltage drop exceeding 3% at the farthest outlet for power, heating, and lighting loads, or exceeding 5% for feeders. Voltage drop is a loss of voltage in an electrical circuit due to impedance. Impedance is the measure of opposition to alternating current. If the voltage drop is too high, this could cause equipment to not operate correctly. Motors may overheat and burn up, lights may be dim, and heaters may not heat properly. Section 215.2a on and Section 210.19a on FPN number 4 contain the recommendation for voltage drop. The formula for voltage drop for a single-phase circuit is voltage drop equals 2x length x current x impedance /1000. The formula for voltage drop for a three-phase circuit is voltage drop equals 1.732x length x current x impedance /1000. Length is the length of the conductor in feet. Current is the load current in amps. Impedance is the impedance of the conductor in ohms per 1000 feet. The NEC does not mandate voltage drop calculations, but it is a good idea to do the calculations to ensure that the equipment will operate correctly. Article 250 contains all the requirements for grounding and bonding. Grounding is connecting the electrical system to the earth. Bonding is connecting all the metal parts of the electrical system together to create a low impedance path for fault current. Grounding helps to stabilize the voltage during normal operation and provides a path for fault current to return to the source. Bonding ensures that all metal parts of the electrical system are at the same voltage potential. If there is a fault, the fault current will flow back to the source and trip the overcurrent protection device. If the metal parts are not bonded together, then a person could get shocked if they touch a metal part that is energized. The size of the grounding electrode conductor is based on the size of the service entrance conductors. Table 250.66 is used to determine the size of the grounding electrode conductor for alternating current systems. For example, if you have 4/0 copper service entrance conductors, then you need a number 2 copper grounding electrode conductor. The size of the equipment grounding conductor is based on the size of the overcurrent protection device. Table 250.122 is used to determine the size of the equipment grounding conductor. For example, if you have a 20 amp overcurrent protection device, then you need a number 12 copper equipment grounding conductor. The equipment grounding conductor is used to ground metal parts of the electrical system that are not designed to carry current. This includes metal enclosures, metal conduit, and metal equipment. If there is a fault, the fault current will flow back to the source through the equipment grounding conductor and trip the overcurrent protection device. Conductors must be protected against physical damage. Article 300.4 goes over protection against physical damage. Conductors can be protected by installing them in conduit, using metal-clad cable, or by installing them in a protected location. Conductors that are installed in exposed locations must be protected from physical damage. For example, if you have a cable running across a wall in a warehouse, it must be protected by conduit or some other means. Conductors that are installed underground must be protected from physical damage. This can be done by installing them in conduit or by burying them deep enough so that they are not damaged by digging. Conductors that are installed in wet locations must be suitable for wet locations. Conductors that are installed in direct sunlight must be sunlight resistant. Conductors must be identified by color. Article 200.6 goes over the requirements for conductor identification. The grounded conductor must be white or gray. The ungrounded conductors must be any color other than white, gray, or green. The equipment grounding conductor must be green or bare. Conductors can be identified by color coding the insulation or by marking the conductors with color tape. Conductors must be spliced properly. Article 110.14b goes over the requirements for making connections and splices. Conductors must be spliced using listed splicing devices that are suitable for the conductors being spliced. Wire nuts, crimp connectors, and terminal blocks can be used to splice conductors. Conductors must be spliced in a way that does not damage the conductors. The insulation must not be damaged and the conductors must be securely fastened together. Conductors must be supported properly. Article 314.17 goes over the requirements for supporting conductors. Conductors must be supported so that they do not sag or come into contact with other objects. Conductors can be supported by using cable ties, cable clamps, or by installing them in conduit. Conductors that are installed in conduit must be supported within 3 feet of each box, fitting, or termination. Conductors that are installed in free air must be supported every 4.5 feet. Conductors must be installed in a neat and workmanlike manner. Article 110.12 goes over the requirements for neat and workmanlike installations. Conductors must be installed in a way that is safe and easy to maintain. Conductors must be installed so that they do not create a hazard. Conductors must be installed so that they do not obstruct access to equipment. Conductors must be installed so that they do not damage other equipment. Electrical installations must comply with all applicable codes and standards. The National Electrical Code is the most widely used electrical code in the United States. The NEC is updated every 3 years. Electrical installations must also comply with all applicable local codes and standards. Local codes and standards may be more stringent than the NEC. It is important to consult with a qualified electrician to ensure that your electrical installation complies with all applicable codes and standards. Understanding these fundamental concepts and adhering to the NEC guidelines are crucial for ensuring electrical safety, preventing hazards, and creating reliable electrical systems. By considering conductor ampacity, termination temperatures, continuous loads, paralleling conductors, dirting, voltage drop, grounding, bonding, protection against physical damage, proper identification, splicing techniques, support methods, and neat workmanship, you can contribute to safe and efficient electrical installations. Also remember to consult with qualified electricians when dealing with electrical installations. The licensed electricians will make sure that everything is up to code and safe for the occupants.